Picture the darkest room you have ever stood in, not dimly lit, truly dark, the kind of darkness where you hold your hand in front of your face and feel the absence of it rather than see it. Now imagine that something in that room is moving toward you, not toward the light switch, not toward the door, toward you specifically with the mechanical patience of a thing that has never needed to be in a hurry. You know it is there only because of the sound of your own breathing changing pitch, only because the hair on your arms is responding to an instinct older than language. Something pulls at you, bends the air around itself, warps the floor beneath your feet, and yet, no matter how hard you strain your eyes, no matter how long you wait for your vision to adjust, there is nothing to see. There never was. That is what a black hole does to a star. And in July of 2026, after 36 years in orbit and more than 1.6 million observations of the cosmos, NASA's Hubble Space Telescope sent back data that stopped the astronomical community cold. A star 18,000 light-years away, tucked inside the densest, most ancient gravitational neighborhood in our entire galaxy, was moving in a way that made no sense. It was tracing an orbit, a measurable, trackable, mathematically precise orbit, around something that produces no light, no radio waves, no X-rays, something that does not announce itself to any instrument ever built, something that our most sensitive orbital telescopes can measure only by the shadow it casts in the motions of others. A star, orbiting something that isn't there, or rather, something that is very much there. Something that was born in the death scream of a collapsing star 12 billion years ago. Something that weighs 4.46 times the mass of our own Sun, compressed into a volume so small it vanishes from the laws of ordinary physics. Something that, until now, had escaped every net astronomers had ever thrown into the dark. How do you find an object that refuses to be found? How does a telescope that looks at light detect something that produces none? And what does this one discovery, this single star tracing one impossibly slow, 94-year orbit around an invisible companion, tell us about the 9,999 black holes still hiding in that same cluster, and the gravitational waves they may one day unleash on the universe? Those questions have answers, some of them. And the ones that don't have answers yet are the ones that will shape the next century of astronomy. There is a moment in every science education. It might come in a classroom, or late at night with a library book, or from a documentary playing on a television in a house that was otherwise dark, when the concept of a black hole stops being a metaphor and becomes a physical reality. For most people, that moment arrives with a certain pleasant terror, a region of space so dense, so warped by the concentrated weight of its own collapsed matter, that not even light, the fastest thing in a universe that has been expanding for 13.8 billion years, can accumulate enough velocity to escape its gravity. The universe's ultimate one-way door, the point of no return. We know about black holes the way we know about a great many things that cannot be directly touched, by the evidence they leave behind in what surrounds them. A black hole, in its quiescent state, sitting in the dark, accreting nothing, announcing itself to nobody, is genuinely invisible. It neither emits nor reflects radiation of any kind. It is not dark in the way that a rock is dark, where the darkness is simply an absence of luminosity. It is dark in a more fundamental sense. It is a region where the rules of geometry have changed so dramatically that the concept of looking at something simply does not apply. Light that crosses the event horizon, that last, invisible boundary, is not absorbed or reflected. It falls inward forever, toward a mathematical point of infinite density that our best current theories cannot describe. John Michell, an English country parson who was also, somewhat improbably, one of the great theoretical minds of the 18th century, first put this idea into words in 1783. He called them dark stars. He reasoned quite correctly that if a body were dense enough, the escape velocity from its surface would exceed the speed of light. Whatever light this body generated would fall back down. The star would become invisible. Michel even had the foresight to suggest, in that same paper, the precise method by which such an object might someday be detected. If one of these dark stars had a luminous companion in orbit around it, the motion of that companion would betray the dark star's presence, not by looking at the dark star, by watching what the dark star does to the light. That was 1783. It took another 191 years, and the construction of orbiting X-ray telescopes, and a paradigm revolution in our understanding of general relativity, and the discovery of neutron stars, and 4 generations of increasingly sensitive optical instruments, before astronomers confirmed the first stellar mass black hole from the behaviour of its companion. The object was Cygnus X1, and its discovery in 1972 via X-ray observations from the Uhuru satellite gave the first hard evidence that black holes were not merely theoretical curiosities, but genuine physical constituents of the universe. Its companion star, HDE 226868, orbited the invisible object with a period of 5.6 days, and the system blazed in X-rays as gas stripped from the companion's outer layers spiraled inward through an accretion disk heated to tens of millions of degrees. This was the template. This was how black holes were found for the next half-century. You looked for the glow, you waited for the X-ray flare, you listened for the radio emission from a relativistic jet, you watched for the telltale oscillation in a companion star's light, the Doppler shift in its spectral lines that revealed it was moving toward and then away from you in a rhythmic cycle governed by the invisible pull of something massive at the centre of its orbit. All of these methods share a common principle. You are not detecting the black hole. You are detecting the evidence of accretion, matter falling onto the black hole, releasing energy as it fell, and announcing its imminent destruction with one last blaze of radiation. This is, to my mind, one of the most quietly astounding facts in all of astrophysics. Virtually every black hole we have ever found, we found because it was eating something. The quiescent black hole, sitting dark and silent, not currently consuming anything, not surrounded by a glowing disk of superheated gas, not blasting a jet of charged particles into space, was essentially undetectable by any method then available to us. Its existence could be inferred from computer models of stellar populations and cluster dynamics. It could be theorized, argued for, expected with high confidence. But it could not be seen and it could not be proven. This is the central irony in what follows. Omega Centauri, the most massive globular cluster in the Milky Way galaxy, a place that our best simulations confidently estimate should contain approximately 10 zero-stellar mass black holes, had never yielded a single confirmed one, not one, in decades of searching. And the reason is that essentially all of those black holes are doing exactly what black holes do when they are not actively feeding. They are sitting in the dark, patient and invisible, waiting to be found by a method that nobody had yet applied to this particular problem. The method that finally cracked this problem is called astrometry. And the Hubble Space Telescope, orbiting 547 kilometers above the surface of the Earth at 27,300 kilometers per hour, was the only instrument in history capable of delivering it at the precision required. But before we can understand why this particular discovery is so arresting, we need to understand the place where it happened. We need to understand Omega Centauri. Omega Centauri is not a place that rewards brevity in description. It is the largest, heaviest, oldest, and most complex stellar structure in our galaxy's retinue of globular clusters, and it has the kind of history that makes most astronomical objects seem straightforward by comparison. Located approximately 18,000 light-years from Earth in the constellation Centaurus, it is visible to the naked eye from the southern hemisphere as what appears to be a slightly blurry fourth-magnitude star, an easy binocular target, a soft smear of ancient light that has been travelling toward your eyes since it left those stars roughly 18,000 years ago, at a time when the most technically advanced human beings on Earth were producing exquisite cave paintings at Lascaux. It was catalogued by Ptolemy nearly 2,000 years ago, listed in his Great Star Catalogue as a single point of light in Centaurus. Edmund Halley, the same man who calculated the period of the comet that bears his name, identified it as a non-stellar object in 1677, noting that it appeared extended, nebulous, not the clean point of light a genuine star would produce through his telescope. In the 1830s, the polymath John Herschel resolved it into individual stars from the Cape of Good Hope, and understood it for what it was, a spherical aggregation of stars of staggering density, a gravitationally bound swarm whose members moved together through space as a single vast family. The number of stars in Omega Centauri is approximately 10 million. That is not a round number offered as a convenience. The current best estimate is 10 million gravitationally bound members, all orbiting their common centre of gravity, packed most tightly in the core, where the density of stars reaches levels that would make the night sky from any planet in that region as bright as a moonlit evening on Earth, and far, far more hazardous for the long-term stability of any solar system. The cluster spans roughly 150 light-years in diameter. At 18,000 light-years, it subtends about half a degree on the sky, the same angular size as a full moon, which makes it one of the most extended and impressive objects in the southern sky. Its total mass is estimated at 3.6 million solar masses, making it the most massive stellar system in the Milky Way known to date. But the numbers that matter most for this story are not the ones describing its size or stellar population. The numbers that matter are these: 12 billion years and 10,000. 12 billion years is the estimated age of Omega Centauri. The universe itself is 13.8 billion years old. Omega Centauri formed when the universe was barely 2 billion years old, before the Milky Way galaxy had settled into its current elegant spiral structure, in an era of cosmic history so remote that the elements required to build rocky planets, carbon, oxygen, silicon, and iron, were present in only tiny trace amounts compared to today. The stars in Omega Centauri formed from gas that was predominantly hydrogen and helium, the original legacy of the Big Bang, with only the merest dusting of heavier elements forged in the first generation of massive stars. This low metallicity, astronomers' term for the abundance of elements heavier than helium, has profound consequences for the kinds of objects the cluster's stars produce when they die. Massive stars in metal-poor environments have weaker stellar winds. They lose less mass during their lifetimes, and when they collapse at the end, they leave behind heavier remnants than their metal-rich counterparts would. In theory, the low metallicity of Omega Centauri means that its black holes should, if anything, be larger than average, not smaller. The number 10,000 refers to the estimated population of stellar mass black holes that should currently reside within Omega Centauri, according to dynamical models of the cluster's evolution over its 12 billion year history. These models are not idle speculation. They are the product of decades of increasingly sophisticated N-body and Monte Carlo simulations that track how a massive stellar population evolves over cosmic time, accounting for stellar birth, stellar death, the formation of compact remnants, gravitational interactions between cluster members, tidal stripping by the Milky Way's gravitational field, and the complex, chaotic dance of stars and black holes within the dense cluster core. The models agree there should be roughly 10,000 stellar mass black holes in Omega Centauri right now, sitting in the dark, invisible, waiting, and yet, before July 2026, not a single one had been found. This is the missing black hole problem in its most concentrated, most vexing form. Not a theoretical absence, but an observational one. The black holes should be there. The physics demands their presence, the simulations predict them, and every observational survey using every technique available had come back empty-handed. Radio surveys, X-ray surveys, radial velocity spectroscopy, photometric surveys looking for X-ray transients, all of it nothing. A cluster of 10 million stars, 12 billion years old, almost certainly hosting 10,000 of the most extreme objects in the physical universe. And we had found precisely 0 of them. What does it mean to find nothing when the mathematics screams that something should be there? The answer to that question occupied some of the best minds in stellar astrophysics for the better part of 3 decades. And the answer, it turns out, had nothing to do with the black holes being absent. It had everything to do with what they were doing while we were looking, and how we were choosing to look. Consider the peculiar frustration of being a field scientist whose subject of study is defined by its invisibility. The particle physicist can at least point to a detector trace, a curved track in a cloud chamber, a signal peak in a histogram, and say, there it is, the thing we were looking for. The geologist has rock samples. The marine biologist has a specimen preserved in formaldehyde. Even the cosmologist, dealing in timescales and distances of almost incomprehensible magnitude, has the cosmic microwave background radiation, that ancient fingerprint of the Big Bang rendered visible by modern instruments, something that can be pointed at on a map and said, this is the echo of creation, and I can show it to you. The black hole astronomer searching for quiescent objects has none of these consolations. The thing being searched for is defined at its most fundamental level by its refusal to leave evidence. This is why the history of black hole detection in globular clusters reads less like a progressive triumph of observation and more like a long accumulation of sophisticated failures, each one more illuminating than the last, each one pushing the community toward the method that would finally work. Understanding those failures is not merely background colour for the story of OmegaCat BH2. It is the story, because the reason this discovery matters so profoundly, the reason it reframes decades of accepted models, is inseparable from understanding why everything that came before it found nothing. The first and most obvious method for finding black holes in globular clusters was looking for X-ray emission. This approach has a pedigree stretching back to the 1970s and the Uhuru satellite, first instrument dedicated to X-ray astronomy. The principle is elegant. A black hole paired with a companion star in a tight binary orbit will, over time, gravitationally strip matter from that companion's outer layers. This transferred matter does not fall directly onto the black hole. Instead, angular momentum causes it to form a disk of spiraling gas, the accretion disk, that contracts ever closer to the event horizon while simultaneously heating through viscous friction to temperatures exceeding 10 million degrees. At those temperatures, matter does not radiate in visible light or infrared or ultraviolet. It blazes in X-rays, and it blazes with luminosity that can briefly outshine every star in its host galaxy. These systems are called X-ray binaries, and they are among the most energetically violent objects in the universe, short of active galactic nuclei and gamma-ray bursts. Omega Centauri has been surveyed repeatedly and deeply in X-rays. The Chandra X-ray Observatory, NASA's flagship X-ray telescope, launched in 1999 and still producing exceptional science in 2026, has imaged the cluster to extraordinary depth, reaching unabsorbed flux limits of approximately 2 × 10 megaergs per second per square centimetre in the 0.5 to 4 5V bandpass. Multiple surveys have been conducted. The results have been consistent. No X-ray source in Omega Centauri has been identified as a stellar mass black hole binary. There are X-ray sources in the cluster, as there are in any massive globular cluster, accreting neutron stars in low-mass X-ray binary systems, cataclysmic variables, chromospherically active stars, but the distinctive signature of an accreting stellar mass black hole, absent. The radio surveys have been equally thorough and equally unrewarding. The Maverick survey, conducted with the Australia Telescope Compact Array and the Carl G. Jansky Very Large Array, represents the deepest systematic radio survey of southern galactic globular clusters ever undertaken. Its published results for Omega Centauri include 29.4 hours of on-source integration time at a central frequency of 7.25 GHz, reaching a 3 sigma upper limit of 8.8 microjanskis. Nothing at the position of any candidate black hole binary was detected. Recent deeper follow-up observations by Mahida et al., published in 2025, pushed that limit lower still, to 3.3 microjanskis. Still nothing. The silence was not from a lack of sensitivity. The instruments were listening hard enough. The black holes were simply not speaking. Why not? This is where the theoretical picture becomes genuinely instructive. and where it reveals the crucial flaw in the detection strategy that astronomers had been using for decades. The X-ray and radio approaches both depend on the same underlying assumption that the black hole in question is actively accreting matter. An X-ray binary blazes because matter is falling onto the black hole right now. A radio-bright black hole is producing a jet because it is currently consuming enough material to drive one. But the rate of accretion in a stellar mass black hole binary is not constant, it is highly variable. These systems cycle between active and quiescent states over timescales ranging from months to decades, and in their quiescent state, which is, for most black holes in most clusters, most of the time, they produce almost no X-ray or radio emission at all. The faintest known quiescent stellar mass black holes, systems like A0620 in its deep quiescence, radiate at luminosities so low that current instruments could not detect them even in a cluster as nearby as Omega Centauri. There is a deeper problem still, and this one strikes at the very heart of what it means to search for something in a dense stellar environment. Omega Centauri has approximately 10,000 stellar mass black holes, but those black holes are not uniformly distributed throughout the cluster. By the iron logic of gravitational dynamics, specifically the process called mass segregation, in which heavier objects sink toward the centre of a gravitational potential well, while lighter objects are preferentially scattered outward. The black holes should concentrate in the densest, most central regions of the cluster. The core of Omega Centauri contains hundreds of thousands of stars packed into a volume roughly 30 light-years across. The stellar density there is extraordinary, the gravitational environment violently chaotic, and the probability of a black hole being in an X-ray bright accreting binary at any given moment is, according to the most careful models, extremely low, not because black holes there are rare, but because the conditions required for sustained detectable accretion are themselves rare events in the statistical sense. The third method that had been applied, and that had produced the only prior confirmed stellar mass black holes in galactic globular clusters, was radial velocity spectroscopy. This is the same technique used to detect thousands of exoplanets. If a star has an invisible companion, the gravitational pull of that companion will cause the visible star to wobble back and forth in space, alternately approaching and receding from our line of sight. A spectrograph can measure this motion with great precision by tracking the Doppler shift of known spectral lines. The characteristic absorption features that elements in a star's atmosphere imprint on the light passing through them. A star moving toward you shows those lines shifted toward shorter, bluer wavelengths. A star moving away shows them shifted toward red. Monitor the star long enough, and the pattern of the shift traces out the orbit. This method produced the only two prior confirmed black holes in galactic globular clusters, both in the metal-poor cluster NGC 3201. Benjamin Giesers and his team at the Georg August Universität Göttingen, using the Muse integral field spectrograph on the Very Large Telescope in Chile, announced the first in 2018. A detached binary system in which a main sequence star with a mass of about 0, 8 solar masses orbited a dark companion with a minimum mass of 4.36 solar masses in a 167-day orbit of extraordinary eccentricity. The second, announced in 2019, was in a dramatically shorter 2.2-day, low eccentricity orbit. Both were extraordinary discoveries. Both were made using the same radial velocity technique that has served exoplanet hunters for 3 decades. But radial velocity spectroscopy has a critical limitation that makes it poorly suited to finding the missing thousands in Omega Centauri. It works best for binary systems with short orbital periods, days to months, because you need to observe the star's velocity change over the course of its orbit, and practically speaking, you need to observe at least a substantial fraction of the complete orbit to be confident in your solution. A system with an orbital period of 94 years is not going to reveal itself through radial velocity measurements taken over a few years of survey work. The star's velocity will change over the observation period, yes, but it will change so slowly, so incrementally, that it will appear essentially constant to a radial velocity survey that does not have both extraordinary precision and a baseline measured in decades. The longer the orbit, the larger the separation between the two objects. The larger the separation, the lower the orbital velocity. The lower the orbital velocity, the smaller the Doppler shift, and the smaller the Doppler shift, the harder it is to distinguish from the noise floor of the measurement. There is also a geometric bias built into the radial velocity method that compounds this problem. Radial velocity only measures motion along the line of sight, the component of the star's velocity that is aimed directly toward or away from the observer. Motion that is perpendicular to the line of sight produces no Doppler shift at all. A binary system seen face-on, where the plane of the orbit is perpendicular to our line of sight, so that both stars always move perpendicular to our direction, produces zero radial velocity signal. The star appears stationary in velocity space even as it moves continuously around its orbit. This is a known and fundamental limitation. It means that at any given moment, a fraction of all binary systems, those with orbital inclinations close to face-on, are simply invisible to the radial velocity method, regardless of how massive the dark companion is. The MUSE Radial Velocity Survey of Omega Centauri, one of the deepest spectroscopic surveys of any globular cluster ever undertaken, found no candidate black hole binaries. Another radial velocity survey, published in 2025, extended this null result further. The community was not surprised. The theoretical models had already begun to suggest why. The radial velocity surveys, for all their depth and precision, were simply not sensitive to the parameter space where most of the cluster's black hole binary population was expected to live. The black holes were not in short-period X-ray binaries. They were not in the narrow velocity range accessible to the surveys. They were in wide, slow, quiet orbits, periods of years or decades, traceable not through the velocity of stars but through the positions of stars, not through how fast a star is moving along the line of sight, but through where the star is in the sky, year by year, compared to where it was before. This is astrometry. And this is where the story changes. The word astrometry comes from the Greek words for star and measure. It is among the oldest branches of astronomy. Hipparchus of Nicaea was doing it in the 2nd century BC, cataloguing the positions of stars with enough precision to notice that the sky appeared to have shifted since the measurements of Timocharys made 150 years earlier, a discovery that eventually led to the recognition of the precession of the equinoxes. For most of its history, astrometry was the most precise science available to observers of the heavens. The positions of stars were known to arcsecond precision before any other astronomical quantity could be measured. But the precision required to detect the wobble of a star being tugged by an invisible companion 3 to 5 times the mass of the Sun, in an orbit with a period of decades, from a distance of 18 0 light-years, that precision is not measured in arcseconds, it is measured in milliarcseconds, or, in the case of the data that led to OmegaCat BH2, in fractions of a milliarcsecond. It is measured, as Matthew Whitaker of the University of Utah put it, down to a fraction of a pixel on Hubble and Webb's detectors. The fact that such precision is achievable from an orbital telescope is, in its own right, a remarkable testament to what the Hubble Space Telescope represents as a scientific instrument. But achieving that precision in the core of Omega Centauri, where the stellar density is so extreme that stars separated by fractions of an arcsecond overlap in the images, where the point spread function of every star bleeds into its neighbours, where the photon noise from the surrounding stellar crowd contaminates every measurement, required not merely good instruments but 20 years of methodological development, of painstaking software construction, of algorithms refined over thousands of hours of analysis. The project that finally made this possible was called OmegaCat. The OmegaCat project did not set out to find a black hole. It set out to understand a star cluster. This is the way science actually works most of the time. The discovery that rewrites the textbooks is rarely the one that was planned for. The planners were trying to do something valuable but modest. compile the most comprehensive astrometric and photometric catalogue of Omega Centauri ever assembled, using the archival resources of the Hubble Space Telescope. The serendipity came later in the data, in the scatter of star positions across 20 years of accumulated exposures, in the discovery that one of those 10 million stars was not moving the way it should, but the foundation, the Omega Cat dataset itself, deserves to be understood as an achievement in its own right before we arrive at the black hole. Because without understanding what it cost to build this catalogue, the discovery at its centre cannot be properly appreciated. The Hubble Space Telescope was launched on April 24, 1990, from the Space Shuttle Discovery, deployed into an orbit 547 kilometres above Earth's surface. Its primary mirror, a precisely ground, 2.4-metre diameter disc of ultra-low expansion glass coated with a microscopically thin film of pure aluminium and magnesium fluoride, was famously too flat, a spherical aberration of 2.2 micrometers, a deviation smaller than 1/50th of the width of a human hair, rendered its initial images blurry rather than sharp. The most expensive telescope ever built, launched after decades of development and political struggle, was for its first 3 years unable to deliver on its transformative scientific promise. The fix came in December 1993, when Space Shuttle Endeavour carried a crew of 7 astronauts to rendezvous with Hubble in orbit and install corrective optics. The corrective optics Space Telescope axial replacement, or COSTAR, that bent the light from the flawed mirror in precisely the right way to compensate for its error. The images that came back after that servicing mission were not merely better. They were revelatory, sharp, deep, capable of resolving structures at angular scales inaccessible from any ground-based telescope. It is one of the more poignant facts in the history of Hubble that the very flaw that caused its initial embarrassment was, in a sense, its greatest advertisement. The before and after photographs, the blurry, smeared images from the first 3 years versus the crystalline precision of the post-servicing views, demonstrated to the public with visceral clarity what the telescope was capable of when it was working correctly. The repair mission became one of NASA's most celebrated achievements, and Hubble became one of the most beloved scientific instruments in human history. By the time the Omega Cat project began mining its archival data, Hubble had accumulated more than 2 decades of observations of Omega Centauri, spread across multiple instruments, multiple epochs, multiple wavebands. The initial data used in the project came primarily from the Wide Field and Planetary Camera 2, installed during the first servicing mission in 1993 and used for 10 years before being replaced by the Advanced Camera for Surveys during the 2002 servicing mission, and from the Advanced Camera for Surveys itself, which delivered substantially improved image quality, sensitivity, and field of view compared to its predecessor. The Hubble observations of Omega Centauri, spanning the project's baseline, ranged from 2002 to 2023, a period of 20.6 years, over which 351 individual epochs passed quality cuts, stringent enough to be included in the astrometric analysis. Let that number settle for a moment. 351 individual measurements of the position of a single star, spread over more than 20 years, from a telescope operating in the darkness of space beyond the atmosphere that blurs and smears ground-based observations into imprecision. This is not a dataset assembled for the purpose of finding one particular star. The Omega Cat catalogue ultimately measured the positions and proper motions of 1.4 million individual stars in Omega Centauri. 1.4 million. Each one measured across multiple epochs, each position refined through a software pipeline that corrected for geometric distortion in the camera, for the proper motion of the cluster itself through space, for the internal rotation of the cluster about its own axis, for the slow drift of the telescope's optical components over time. Maximilian Heberle at the Max Planck Institute for Astronomy in Heidelberg led the data reduction effort, a task of extraordinary technical complexity and patience, and the resulting catalogue was published in 2024. It was the highest quality space-based astrometric dataset for any galactic globular cluster that had ever been assembled, the catalogue immediately began producing science. Using the proper motions of stars near the centre of Omega Centauri, particularly the handful of stars moving fast enough to be accelerated by an extremely massive central object. Hubble and colleagues published strong evidence for the existence of an intermediate mass black hole at the cluster's centre in the journal Nature in 2024. The estimated mass of this central behemoth was 8,200 solar masses, making it the closest known intermediate mass black hole to Earth, closer even than the 3 million solar mass supermassive black hole at the centre of our own Milky Way, Sagittarius A. This result, published in June 2024, made headlines worldwide and cemented Omega Centauri's status as the most scientifically consequential globular cluster in the sky. But the same dataset that revealed the intermediate mass black hole also held something else, something subtler, something that required not the screaming velocity of stars passing within fractions of a light year of an 8200 solar mass object, but the patient, slow curve of a star nudged, over months and years, by a much smaller invisible companion, a companion weighing 4.46 solar masses. Moving on a timescale not of days or hours but of decades, the search for this object began in a sense with a prior false start, a tantalizing near-miss that illustrates both the difficulty of the problem and the way in which science advances by building on its own failures. In 2024, a team led by Platers and colleagues published a study that used an independent reduction of a subset of the long baseline Omega Centauri HST astrometric data to identify 4 candidate astrometric binaries with dark companions. Their analysis inferred masses for these companions consistent with white dwarfs or possibly neutron stars. One of these 4 candidates, a main sequence star later identified as star 285597 in the Hubble et al. 2024 catalogue, appeared in their analysis to be consistent with a neutron star companion, not a black hole. A neutron star. This was a reasonable conclusion given the data available to the Platers team, but their analysis used only a subset of the full Hubble archive, and it lacked the additional temporal baseline provided by the James Webb Space Telescope observations taken in 2024 and 2025. When the University of Utah team, led by Matthew Whitaker with Anil Seth as senior author, incorporated the complete OmegaCat Hubble dataset, augmented with 2 epochs of JWST NIRCam short wavelength observations from 2024 and 2025, the picture changed dramatically. The story of the discovery reads, in the words of one commentator, like a Sherlock Holmes story. You begin with a suspect, a star that is moving strangely. You compile the evidence, 351 Hubble measurements and 12 JWST measurements spanning 23 years. You build the case. A Markov chain Monte Carlo orbital fit to the astrometric data, constrained by a prior on the star's velocity within the cluster, derived from dynamical simulations of an Omega Centauri-like system, and you arrive at a conclusion that is not what the previous investigation found. The visible star, catalogue ID 285597, a main sequence turn-off star with a mass of 0.78 solar masses, roughly 18 zeros light-years away in the dense core of Omega Centauri, was not orbiting a neutron star. It was orbiting a black hole, a stellar mass black hole with a mass of 4.46 solar masses, give or take approximately 1 solar mass in either direction. The orbital period of the binary was 94 years, with substantial uncertainty in the exact value, ranging from perhaps 52 years to 157 years, though the best fit solution centres around 94 years. The semi-major axis of the orbit was approximately 31 astronomical units, roughly the distance between the Sun and Neptune. The orbital eccentricity was 0.72, meaning this was not a gentle circular dance, but a dramatically elongated ellipse, with the star sweeping in close to its dark companion at periastron, closest approach, and then swinging far out into the cluster on the far side of its orbit. The eccentricity is significant for reasons that go beyond orbital mechanics. It tells us how this binary came to exist. Circular or mildly eccentric orbits tend to characterize binaries that form together from the same molecular cloud. systems where two protostars condense from the same rotating disk of gas and have been evolving in gravitational proximity ever since. High eccentricity of the kind seen here is a signature of dynamical formation, an encounter in the dense core of the cluster where two previously unrelated objects, a lone black hole sinking toward the center by mass segregation and a main sequence star orbiting peaceably in the cluster, came close enough at low enough relative velocity that gravity captured them into a bound system. The star did not form with this black hole. The star found this black hole billions of years after both objects came into existence, in a gravitational encounter that no individual observer was present to record. This dynamically formed nature has profound consequences for how long the binary will survive. A primordially formed binary, one that originated together, can persist for the entire lifetime of the cluster, billions of years, if the system is stable and not disrupted by encounters with passing stars. A dynamically formed binary, particularly one with a long orbital period and a relatively wide separation, is soft in the technical vocabulary of stellar dynamics. A soft binary is one whose binding energy is lower than the typical kinetic energy of the surrounding stellar population. In an environment like the core of Omega Centauri, where thousands of stars and potentially thousands of black holes are moving at velocities of tens of kilometers per second, a soft binary will be disrupted, its two components scattered back into the general population, on a timescale far shorter than the age of the cluster. The researchers calculated this disruption timescale for OmegaCat BH2, approximately 800 million years. The cluster is 12 billion years old. The binary is a temporary arrangement, a brief and fragile gravitational partnership that will end, through a chance encounter, a near miss with another massive object in the cluster core, long before the cluster itself disperses. I find this fact genuinely moving, in a way that I did not entirely expect when I first encountered it in the paper. The binary will not last. The star and its dark companion found each other across the immensity of 12 billion years of cosmic history, and they have been locked in this slow, eccentric orbital embrace for some unmeasured time, perhaps tens of millions of years, perhaps hundreds of millions, and they will be separated again by the same chaotic gravitational environment that brought them together. There is something in this that speaks to the impermanence of all arrangements in the universe, even the most powerful and dramatic ones. Everything is temporary, even a black hole binary, even something that bends space-time. But the question that had haunted Omega Centauri for decades was not about the biography of one particular binary. It was about the missing 10,000, and to understand why finding one is so significant, and why it raises the stakes far higher than the discovery of a single object should, mathematically speaking, we need to understand what the models had been predicting and why this single observation both confirms and complicates them at the same time. The models, particularly the cluster Monte Carlo simulations run by the Northwestern University Group, which represent the current state of the art in globular cluster dynamics, had a specific prediction about what stellar mass black hole binaries in Omega Centauri should look like if they existed. They should have a range of companion masses, spanning from very low mass main sequence stars up to stars at the main sequence turnoff. They should have a range of orbital periods, spanning from very short to very long. They should preferentially concentrate in the central regions of the cluster, where mass segregation has driven the black holes. And they should be there in numbers. The simulations of González Prieto et al., published in 2025, which model an Omega Centauri-like cluster with a central intermediate mass black hole growing from a 500 solar mass seed over 12.5 billion years of evolution, end with 2,459 stellar mass black holes still in the cluster, including 9 visible star black hole binaries at the simulation's final timestamp, and 474 such binaries sampled across the last billion years of simulation history. What has been found so far is 1. This is not yet a contradiction. The simulations cover a wide range of parameter space, orbital periods from days to decades, companion masses across the main sequence, and the existing surveys, including both the OmegaCat search and all previous radial velocity surveys, cover only a small fraction of that space. Whittaker and colleagues are explicit about this in their paper. The presence of additional detectable black hole binaries is likely, and the current data only covers a tiny slice of the full parameter space accessible to current instruments. But the single detection, in the context of a predicted 10,000 total black holes and up to 2,459 still in the cluster, raises an immediate and uncomfortable question. If there are thousands of black holes in this cluster, and the dynamical models predict dozens of visible star black hole binaries at any given time, why is this particular binary such a unique detection? The answer lies partly in observational sensitivity. The OmegaCat search, for all its extraordinary precision, is sensitive primarily to the brightest stars in the cluster, those near or above the main sequence turn-off, and to orbital periods of years to decades. Systems with very faint companions, or very short periods, or very long periods extending well beyond the 20-year observational baseline, will be missed. The full census of Omega Centauri's black hole population is not yet accessible. It will require wider, deeper, longer surveys, and that prospect, the prospect of those future surveys and what they might find, is one of the most exciting questions currently hanging over the field. But the single detection has already told us something that no simulation had predicted. The black hole has a lower than expected mass. In a metal-poor environment like Omega Centauri, where the reduced stellar winds of low metallicity massive stars should leave behind heavier black hole remnants, finding a black hole of only 4.46 solar masses, close to the minimum mass for a stellar mass black hole, is, as Anil Seth put it, surprising and exciting. The stellar evolution models for metal-poor environments suggest that massive stars at this metallicity should produce black holes of significantly higher mass. And yet here is a black hole barely above the threshold, sitting in one of the most metal-poor globular clusters in the Milky Way. What happened to the mass that the models predicted? Did the progenitor star lose mass through some mechanism we don't fully understand? Did the supernova that created this black hole involve a neutrino-driven kick that ejected a significant amount of material before the collapse completed? Is the low metallicity of Omega Centauri less determinative of remnant mass than the models suggest? These questions do not yet have answers, but they are exactly the questions that make this discovery something other than a checkmark on a to-do list. They are questions that point toward deficiencies in our models of stellar evolution and black hole formation. Deficiencies that, if we can understand them, will make our predictions about the black hole populations of globular clusters, and about the gravitational waves those populations eventually produce, sharper and more reliable than they currently are. And the gravitational wave connection is where the stakes leave the realm of purely academic curiosity and become something much larger, something that touches the future of our ability to understand the deepest, most violent processes in the universe. Something that turns this one star, orbiting something that isn't there, into a thread that connects to the most profound physics experiments of our age. On September 14, 2015, at precisely 09:50:45 Coordinated Universal Time, two L-shaped detectors, one in Livingston, Louisiana, and one in Hanford, Washington, recorded a signal. The signal lasted 0.2 seconds. It moved the mirrors in those detectors by a distance roughly equivalent to 1/10,000th the diameter of a proton. The signal's frequency swept upward from 35 Hz to 150 Hz in that fraction of a second and then abruptly stopped. When the physicists of the LIGO scientific collaboration analysed this signal against their theoretical templates, they found a match, a nearly perfect match, with what general relativity predicts for the gravitational radiation emitted by two black holes, each approximately 30 solar masses, spiralling toward each other and merging into a single object 1.3 billion light-years away. The merger had released, in that final fraction of a second, more energy than all the stars in the observable universe emit as electromagnetic radiation combined. That energy had crossed 1, 3 billion light-years of space as ripples in space-time geometry itself, gravitational waves, and arrived at Earth as the most energetic event ever directly measured by a human instrument, displacing each mirror in the LIGO detectors by a length that defies everyday analogy. This was GW 15091Phi, the first direct detection of gravitational waves, announced to the world in February 2016. It won the Nobel Prize in Physics in 2017. It opened a new window on the universe, not a window of light, but a window of gravity. And it immediately posed a question that has occupied theorists and observers ever since. Where did these black holes come from? They were massive. 30 solar masses, each as large for a stellar mass black hole, formed through the core collapse of a single massive star, though not impossibly large. But they were paired, and that pairing requires explanation. Two black holes in a tight enough orbit to merge within the age of the universe must either have formed together from the same stellar binary, evolved to the compact object stage while remaining gravitationally bound, or have formed separately and later been brought into a merging orbit through some external dynamical process. For black holes as massive as the GW 1591T pair, the first channel, isolated binary stellar evolution, is possible but requires the progenitor stars to have had very low metallicity, which limits the mass lost to stellar winds and allows them to produce massive black hole remnants. The second channel, dynamical formation in a dense stellar environment, is possible in environments where the density of stars and compact objects is high enough to drive frequent interactions and allow black holes to form bound pairs. The environment most frequently invoked for dynamical formation of massive black hole binaries is the globular cluster. This is not a new idea. Theorists had been discussing it since the 1970s, but the LIGO detections gave it fresh urgency. Rodriguez et al. Published a series of papers beginning in 2015 and 2016 demonstrating through N-body simulations that globular clusters could produce binary black hole merger rates consistent with LIGO's first detection. Their models predicted that clusters like those in the Milky Way could contribute dozens to hundreds of detectable mergers per year to a network of advanced gravitational wave detectors. The key mechanism is straightforward in principle, though extraordinarily complex in the details. A globular cluster acts as a black hole factory, concentrating its heaviest remnants through mass segregation into a dense central subsystem where they interact frequently, form binaries through gravitational capture, harden those binaries through subsequent interactions with other cluster members, and eventually achieve orbital parameters tight enough and energetic enough for gravitational wave emission to drive the two objects to merger within a Hubble time. This is the gravitational wave connection that makes Omega Cat BH2 significant far beyond its status as one black hole among what should be 10,000. To understand and model the expected gravitational wave output from globular clusters, to make reliable predictions about the rate of black hole mergers that LIGO and its successors will detect, and about the mass distribution of the black holes in those mergers, you need to know the actual black hole population of actual clusters, not the theoretical population predicted by dynamical models, but the observed population constrained by direct detection. And the observed population, as of the discovery of Omega BH2, consists of 3 confirmed stellar mass black holes in galactic globular clusters, counting the 2 in NGC 3201, and now the 1 in Omega Centauri, 3 out of an estimated population of hundreds of thousands distributed across the 200-odd globular clusters of the Milky Way. This observational sample is so small that it would be dangerous to draw strong conclusions from it, and the researchers are appropriately cautious. But even a sample of 3 tells you something. The 2 black holes in NGC 3201 were found by radial velocity spectroscopy and have masses in the range of roughly 4 to 10 solar masses. The black hole in Omega Centauri was found by astrometry and has a mass of 46 solar masses. All 3 are at the lower end of the stellar mass black hole mass distribution. None of them are the 30 solar mass objects detected by LIGO, None of them are the 33 solar mass Gaia BH3 found via astrometry of a wide binary in what appears to be a dissolved globular cluster tidal stream. This could reflect a real physical difference between the black holes currently detectable by our methods and the black holes in tight, merging binaries detected by LIGO. Or it could simply reflect the sensitivity limits of the methods. Low-mass black holes in binary systems with observable companions are easier to find than high-mass black holes in compact binaries heading toward merger. The two populations may be talking about completely different portions of the black hole mass function. What makes this uncertainty so consequential is that it matters for one of the most pressing questions in gravitational wave astronomy. Do the black holes detected by LIGO preferentially come from globular clusters, or from isolated stellar binary evolution, or from a combination of both? And if clusters are important sources, which types of clusters and which mass range of black holes dominate the merger rate? These questions cannot be answered from theory alone. They require observational constraints on the actual populations of black holes in the actual clusters that are supposed to be producing these mergers. And those observational constraints, as of 2026, are almost entirely absent. The significance of OmegaCat BH2 is therefore not simply that it is the first stellar mass black hole found in Omega Centauri. It is that it demonstrates the viability of the astrometric method for finding quiescent, non-accreting black holes in globular clusters. It proves that Hubble's 2-decade archive contains the information required to make these detections, and it opens the door to a systematic search, not of one cluster but of every cluster for which comparable archival data exists, that could, within the next decade, produce a statistical sample of black hole binaries in globular clusters, large enough to actually test the theoretical models at the heart of the LIGO interpretation problem. This is why Anil Seth's words in the official announcement carry such weight. It's important to understand black hole populations in globular clusters because there's uncertainty about their physics and formation. More specifically, understanding the process of forming black holes and then dynamically forming binaries is vital because it affects our ability to interpret and understand gravitational wave events. Environments like Omega Centauri are the primary places where we think binaries are merging and creating these waves. This is not a pro forma acknowledgement of broader relevance, the kind of obligatory paragraph that appears in every press release connecting a narrow scientific result to some grander theme. This is a statement of actual scientific necessity. The black hole populations of globular clusters are not peripheral to gravitational wave astronomy. They may be central to it, but there is a complication in the OmegaCat BH2 result that cuts against the simplest version of this story, and it is a complication that the authors themselves flag as one of the most puzzling aspects of their discovery. The black hole's mass is lower than expected. In a metal-poor environment like Omega Centauri, where the theoretical models predict that the reduced mass loss during the stellar evolution of massive stars should leave behind larger black hole remnants, finding a 4.46 solar mass black hole is anomalous. If the stars in Omega Centauri's early history were forming from primordially low metallicity gas, at a metallicity Z01, roughly 1/10 the solar value, then the models of stellar evolution and black hole formation predict that the black hole remnants should be systematically heavier than those formed from solar metallicity stars. This is because heavy stars in metal-poor environments retain more of their mass as they evolve, because weaker stellar winds mean less mass is expelled into space before the final collapse. The result should be more massive black holes, not less. And yet here is OmegaCat BH2 sitting at 446 solar masses, just barely, if at all, above the theoretically proposed black hole neutron star mass gap. The range of masses between approximately 2.5 and 5 solar masses, where compact remnants are thought to be rare due to the specific dynamics of core collapse supernovae. The fact that this black hole sits at the low end of the mass spectrum, in an environment where the models predict the opposite, is either evidence that our stellar evolution models for low metallicity massive stars are missing something important, or evidence that the progenitor of this particular black hole had an unusual evolutionary history, perhaps involving significant mass loss through binary interaction before the final collapse, or evidence that the mass gap itself extends to lower values than we thought, and this object sits just above its upper boundary by coincidence. I will admit, when I first read this section of the paper, I had to put it down and sit with the implications, because the mass gap is one of the most theoretically motivated features of the black hole mass spectrum, and it derives from very specific predictions about how core collapse supernovae work, about how the shock wave propagates through the collapsing stellar core, and whether it successfully unbinds the outer layers, or fails and collapses the entire star into a black hole. Finding an object at the low end of the black hole mass range, in an environment where the models predict high masses, is not a contradiction. It is a data point that says the models need refining, and refining models of black hole formation is not an abstract exercise. It is the groundwork for knowing how many black holes of what mass are being produced across cosmic history, and what that implies for the rate of mergers that LIGO and its future successors will detect as the sensitivity of gravitational wave astronomy continues to improve. There is one more layer to this story that cannot be left unexamined, because it speaks to the peculiarity, the genuine uniqueness, of Omega Centauri as a place. The cluster is not, most astronomers now believe, a genuine globular cluster at all. Or rather, it is a globular cluster now, but it was not born as one. And understanding what it was before it became what it is today changes the entire complexion of the question. What is hiding in there? Matthew Whitaker was a graduate student at the University of Utah when he began working on the analysis that would produce OmegaCat BH2. He was not, in the beginning, a black hole astronomer in any specialist sense. He was a young researcher interested in stellar dynamics and the kinematics of dense stellar systems. Working under the supervision of Anil Seth, whose own research career had wound through studies of dwarf galaxies, ultra-compact dwarfs, nuclear star clusters, and the scaling relations between galaxies and their central black holes. The research group at Utah had existing expertise in astrometry and the dynamics of compact stellar systems, and when the OmegaCat catalogue became available, with its extraordinary baseline of Hubble data reduced to sub-millisecond precision by Heberle and his colleagues at the Max Planck Institute for Astronomy, they began a systematic search for astrometric binary systems in the cluster. The search was not trivial. To find a binary system through astrometry, you need to be able to see the reflex motion of the visible star, the tiny, slow wobble induced by the gravitational pull of its invisible companion, against the background of the cluster's own proper motion. This means you need to know the cluster's proper motion to extraordinary precision, which requires modelling the motions of the thousands of other stars in the field simultaneously with the motion of your target. The star you are tracking is not sitting still against a fixed background. It is moving through the cluster, and the cluster is moving through the galaxy, and the galaxy is moving through the local group, and all of these motions are superposed on the reflex wobble you are trying to measure. Separating the wobble from the bulk motion is a computational and statistical challenge of considerable depth. Whitaker built the fitting machinery, a Markov chain Monte Carlo orbital fitting code capable of simultaneously constraining the orbital parameters of a binary system while marginalizing over nuisance parameters, describing the star's proper motion within the cluster and the measurement uncertainties of individual epochs. The MCMC approach is ideal for problems of this kind, because it does not seek a single best fit solution, but rather maps out the entire probability distribution of solutions consistent with the data. Given the 23-year baseline, the fact that the binary's orbital period is itself uncertain and likely longer than the baseline, the MCMC provides a proper accounting of all the ways in which the data could be explained, including orbital periods much longer than 94 years, and shows that within the range of viable solutions, The companion's mass is high enough consistently and across the full posterior distribution to rule out a neutron star and confirm a black hole. The JWST data played a crucial role in this conclusion. The two epochs of James Webb Space Telescope observations from 2024 and 2025, obtained with the NIRCam instrument in its short wavelength channel, added leverage to the orbital solution at exactly the right phase. The binary system was observed during periastron, the closest approach of the visible star to its black hole companion, when the orbital velocity is highest and the astrometric motion is most rapid. The JWST data confirmed and refined the Hubble measurements at this critical phase, providing the most precise positional constraints in the dataset at the very moment when the star's position was changing most rapidly and most informatively. Without the JWST data, the mass constraint on the companion would have been weaker, perhaps ambiguous enough to allow a neutron star explanation to survive. With it, the black hole identification was secure. The precision required for this measurement borders on the incomprehensible when translated into physical terms. The star in question lies 18,000 light-years away. 1 light-year is approximately 9.46 times 10 squared kilometers. The star is thus approximately 1.7 times 10 flaf kilometers from Earth. The astrometric wobble being measured, the tiny displacement of the star's position on the sky due to the gravitational pull of its black hole companion, corresponds, at that distance, to a physical displacement of perhaps a few astronomical units per year at maximum. An astronomical unit is 149.6 million kilometers. A few astronomical units at a distance of 1.7 times 10 kilometers subtends an angle on the sky of approximately 1/10 of a milliarcsecond. 1 milliarcsecond is 1,000th of an arcsecond. 1 arcsecond is 1/3/600th of a degree. The full circle of the sky spans 360 degrees or 1,296.00 arcseconds or 1,296,000 milliarcseconds. The signal being measured is approximately 1/10,000,000th of that full circle. This is what Whittaker meant when he said the precision was down to a fraction of a pixel on Hubble and Webb's detectors. The pixels on Hubble's advanced camera for surveys subtend approximately 0.05 arcseconds on a side, 50 milliarcseconds. To measure positions to 1/10 of a milliarcsecond requires locating the centroid of a star's light distribution to better than 1/500th of a pixel. This is achievable through statistical combination of many measurements. The random noise averages down as the number of observations increases, following the square root rule of statistics, but it requires extraordinary cleanliness in the measurement process. Any systematic error in the centroiding, any distortion in the point spread function that is not fully accounted for by the Kepler-Dremschen model, any contamination from the light of neighbouring stars in the dense cluster core will masquerade as a real astrometric signal and either create a false detection or corrupt a real one. The work that went into characterizing and correcting these systematic effects over years of software development and calibration work is invisible in the final published result, but absolutely foundational to its credibility. But set aside the instrumentation for a moment. Set aside the computation, set aside the 23 years of archival data and the months of MCMC sampling and the careful derivation of orbital posteriors. Think instead about what was discovered and where it was discovered, because the place is as extraordinary as the discovery. Omega Centauri is, with high probability, not a globular cluster, not in origin, not in the sense that a cluster like 47 Tucanae or NGC 3201 is a globular cluster, born from a single event of star formation within the halo of the Milky Way, carrying the chemical signature of one population of stars formed at one time from one reservoir of gas. Omega Centauri has at least 5 distinct stellar populations, perhaps as many as 15, each with slightly different chemical compositions and ages, spread over a range spanning perhaps 2 billion years of star formation history. No ordinary globular cluster produces multiple stellar generations. The dense, hot, radiation-intense environment of a newborn globular cluster terminates star formation on timescales of a few million years not a few billion. To sustain multiple generations of star formation, you need a deep gravitational potential well capable of retaining the processed gas expelled by the first generation of dying stars. The supernovae and stellar winds that enrich the interstellar medium with heavy elements and seed the next generation. Ordinary globular clusters cannot do this. They are not massive enough. Their escape velocities are too low. There is exactly one type of object that can sustain this multi-generational star formation that has the depth of potential well required to hold on to chemically enriched gas over billions of years, that can build the complex multi-population stellar system we observe in Omega Centauri, the nuclear star cluster at the centre of a dwarf galaxy. The stripped nucleus, the frozen heart of a once-living galaxy that fell into the gravitational embrace of the Milky Way billions of years ago, had its outer stellar envelope torn away by tidal forces as it spiraled inward, and left only its densest, most tightly bound central core behind. The nuclear star cluster, now orbiting the Milky Way as what appears for all the world to be a globular cluster, but is in fact something else entirely. Something that was once, in the remote past of the early universe, the centre of an independent galaxy. The evidence for this interpretation is now broadly accepted by the astronomical community. The multi-population stellar chemistry of Omega Centauri, the anomalously high mass that makes it the largest known globular cluster by a substantial margin, the fact that it harbours what appears to be an intermediate mass black hole of 200 solar masses at its centre, intermediate mass black holes being the characteristic central black holes of dwarf galaxies, and its unusual kinematic, including a retrograde orbit around the Milky Way that suggests it was accreted rather than formed in situ, all point in the same direction. Omega Centauri is the stripped nucleus of a dwarf galaxy consumed by the Milky Way billions of years ago. The galaxy it once was had a name in the formal cataloguing sense, but no observer has ever seen it because the galaxy was already being dismembered before any human eye existed to watch. What remains, these 10 million stars, this 12 billion-year-old remnant of a once-living system, is the heart without the body, the core without the halo, the most massive and most ancient tombstone in the sky. This history has a direct bearing on the black hole question. If Omega Centauri is the nucleus of a former dwarf galaxy, then its black hole population is not merely the remnant of stars that formed and died within an ordinary globular cluster. It is the black hole graveyard of an entire galaxy, a galaxy that was itself massive enough to retain a central intermediate mass black hole, a galaxy whose stellar population spanned billions of years of evolution, generating multiple generations of massive stars, each generation leaving behind compact remnants that sank to the centre, accumulated, interacted, and contributed to the building up of what is now one of the most extreme environments in the local group. The 10 zeros and stellar mass black holes that the models predict should be in Omega Centauri are not the remnants of 10,000 stars that formed in a single episode of star formation. They are the accumulated remnants of billions of years of stellar evolution across an entire, if small, galaxy's lifetime. They represent the full death toll of a stellar system that is 12 billion years old, compacted into a region roughly 150 light-years across by billions of years of gravitational sinking and dynamical friction. There are approximately 2,500 to 10,000 stellar mass black holes, by the best current estimates, still in this cluster right now, moving through the stellar crowd, sinking toward the centre, some of them in brief binary partnerships with normal stars, like OmegaCat BH2, some of them in tight binaries with other black holes spiralling toward each other under the slow drain of gravitational wave emission, destined to merge in millions or billions of years, and send another ripple across the fabric of space-time, to be recorded perhaps by instruments that do not yet exist in their final form, and some of them entirely alone, dark, silent, unpartnered, drifting through the cluster at velocities governed by the depth of the potential well, interacting gravitationally with everything around them but leaving no electromagnetic trace. These solitary black holes, The truly invisible ones, the ones with no companion, no accretion disk, no radio jet, no astrometric wobble to betray them, are the bulk of the population. They are the ones that all prior surveys failed to find. They are the ones that, in the fullness of time, may provide the merging pairs that gravitational wave detectors will hear. To understand why this matters for gravitational wave astronomy, you need to understand the life cycle of a black hole binary in a globular cluster, from formation through hardening to eventual merger. The process is not quick. It unfolds over millions to billions of years, driven by a sequence of gravitational interactions that are individually chaotic but collectively predictable in their statistical behavior. A black hole that has sunk to the center of a cluster through mass segregation begins to interact with other massive objects in the core. If two black holes happen to pass close enough together, with low enough relative velocity, the gravitational two-body interaction may result in their capture into a bound binary. This binary then interacts with other stars and black holes in the surrounding cluster, and each interaction tends, on average, to transfer energy from the binary's orbital motion to the kinetic energy of the intruding object. A process called dynamical hardening. The binary shrinks, the orbital period shortens, the two black holes spiral closer and closer together, their orbit becoming tighter and more energetic with each interaction. This hardening process continues until the binary becomes so tight, the orbital separation so small, the gravitational wave emission so significant, that radiation rather than stellar interactions drives the final inspiral. At this point, the binary is effectively decoupled from its stellar environment. The two black holes circle each other with periods of minutes to hours, radiating energy into space-time at a rate that accelerates as the separation decreases. The final plunge, the merger, is over in seconds, a violent coalescence that converts several percent of the total mass energy of the system into gravitational waves in the last moments before the singularities merge. This is what LIGO hears. This is what happened 3 billion years ago in some dense stellar environment somewhere to produce GW 150914. Whether that dense stellar environment was a globular cluster like Omega Centauri, or a dense nuclear star cluster, or a dwarf galaxy's central region, which amounts in many cases to the same thing, is precisely what we need the observational census of black hole populations in real clusters to determine. And the first entry in that census, OmegaCat BH2, tells us something important and something unexpected, and then leaves us standing at the edge of a much larger problem that the next decade of observations is going to need to address. It tells us the astrometric method works. It tells us quiescent black holes in wide binaries with normal stars exist in globular clusters, at least in Omega Centauri, and they are detectable with existing data if the observational baseline is long enough and the instruments are precise enough. It tells us the black hole in this particular system is less massive than expected, which means our stellar evolution models for low metallicity environments need attention. And it asks us, if this is only one of potentially thousands, what does the rest of the population look like? What are the orbital period distributions, the mass functions, the spatial distributions within the cluster? Are the black holes there in the numbers the models predict, or has something systematically reduced their population below the theoretically expected level? And if they are there, if the full 10,000 are lurking in the dark, a tiny fraction of them in transient binary partnerships, the vast majority entirely alone, what does their presence imply for the gravitational wave sky that future detectors will map? Here is a fact about black holes in globular clusters that I find genuinely haunting, and that is underappreciated in almost every popular treatment of the subject. Even the black holes that have no stellar companion, that are producing no radiation of any kind, that are entirely undetectable by any observational method currently available, even those solitary, invisible, silent objects are not without consequence. They are shaping the cluster around them. They are determining its structure. They are the invisible architects of the world that surrounds them, bending its evolution over billions of years in ways that are measurable not by detecting the black holes directly, but by detecting the effects of their collective mass and energy on the dynamics of the visible stellar population. This is the concept of black holes as structural engineers. It is one of the most important theoretical insights of the last 3 decades of globular cluster research, and it emerged from a long-running tension between observations and models that took years to resolve. The tension was this: globular clusters have a characteristic structural feature called the core, the dense, bright central region where the stellar density peaks before declining gradually toward the cluster's outskirts. In many clusters, this core is extended and diffuse, reaching a size of several parsecs before the density profile turns over. In a minority of clusters, the core appears collapsed. The density rises continuously toward the center, with no distinct turnover, creating what is called a cusp profile rather than a core profile. These core collapsed clusters were understood, for decades, to represent the end state of a dynamical process called gravithermal collapse, in which the random gravitational interactions among cluster stars cause the core to contract steadily over time, concentrating energy in a smaller and smaller volume until the stellar density in the center becomes extreme. But the simulations in the 2000s and 2010s revealed that this simple picture was wrong, or at least incomplete. Clusters that retained a significant population of stellar mass black holes did not collapse. The black holes, concentrated in the cluster core by mass segregation, acted as a heat source, a dynamical pressure system that continually injected energy into the surrounding stellar population through gravitational interactions, preventing the core from contracting. The black hole subsystem was, in the theoretical vocabulary, burning the gravitational potential energy of the cluster, converting it into kinetic energy of the surrounding stars, puffing up the core and maintaining its extended structure against the inexorable tendency of gravity to draw everything inward. Clusters with large black hole populations had large extended cores. Clusters that had lost most of their black holes to dynamical ejection had small, dense cores, the signature of core collapse proceeding once the black hole heat source was gone. This prediction was borne out observationally in the 2010s, when careful comparison of cluster structural parameters with dynamical models revealed a clear correlation. Clusters with large cores were those most likely to retain substantial black hole populations, while core collapsed clusters were those most likely to have expelled their black holes through gravitational interactions over billions of years of evolution. The structure of a globular cluster, the size of its core, the shape of its density profile, the relationship between its core radius and its half-light radius, is, in a real and direct sense, a record of its black hole history. The core is a fossil, a gravitational memory, a visible consequence of invisible objects that may themselves no longer be present. Omega Centauri has a large core. It has an extended, non-collapsed density profile consistent with the retention of a substantial black hole population. And it has the additional complication of its central intermediate mass black hole, the 200 solar mass object that Hubble and colleagues detected through the motions of fast-moving stars in 2024, whose presence adds another source of dynamical heating to the cluster's core, complicating the disentanglement of the stellar mass black hole population structural effects from those of the central IMBH. The theoretical models have not yet fully incorporated both the intermediate mass black hole and a substantial stellar mass black hole population into the same self-consistent dynamical model of Omega Centauri's structure. This is one of the key outstanding theoretical tasks that the observational community is waiting on. A comprehensive dynamical model of Omega Centauri that includes all relevant components, the 10 million visible stars, the central IMBH, the stellar mass black hole population, the white dwarfs and neutron stars and other compact remnants, and produces predictions for what that model cluster should look like observationally at the current epoch, predictions that can be tested against the OmegaCat catalogue and future observations. But the structural argument alone is not the most dramatic evidence for the invisible influence of black holes on their surrounding cluster. That distinction belongs to a phenomenon that connects Omega Centauri's past to the most energetically violent environment in the galaxy, the center of the Milky Way. When a globular cluster or dwarf galaxy falls toward the center of a larger galaxy, tidal forces, the difference in gravitational pull between the near side and the far side of the orbiting object, gradually strip stars from the cluster's outskirts, creating a stream of stars that traces the cluster's orbital path. This tidal stripping is the process that over billions of years has removed the outer stellar envelope from what is now Omega Centauri, leaving only the compact, tightly bound nucleus. But at some point in the past, perhaps several billion years ago, the orbit of the proto-Omega Centauri galaxy brought it close enough to the Milky Way's center that something even more dramatic may have occurred. If the galaxy's central IMBH came within a certain radius of the Milky Way's supermassive black hole, Sagittarius A, gravitational interactions between the two black holes could have scattered stars from the IMBH's immediate environment at extraordinary velocities, high enough that those stars could have been ejected not merely from Omega Centauri, but from the Milky Way galaxy entirely, or sent racing outward through the galactic halo at hundreds of kilometers per second. Hypervelocity stars, stars moving so fast that they are unbound from the Milky Way's gravitational field, escaping into intergalactic space, have been known since 2005, when Jack Hills predicted their existence, and Warren Brown and colleagues found the first example. Most hypervelocity stars are understood to originate from close encounters between stellar binary systems and Sagittarius A at the galactic center, the Hills mechanism in which one star is captured by the black hole, while the other is ejected at extreme velocity. But a subset of these stars has a chemical composition and age distribution inconsistent with an origin at the galactic center. They look, in their stellar populations, like Omega Centauri stars. This has led several groups to propose that some hypervelocity stars may have been ejected from Omega Centauri during a close passage near the galactic center, slung outward by the gravitational slingshot of a black hole encounter between the clusters IMBH and Sagittarius A. If this is correct, then Omega Centauri's black holes are not merely shaping the dynamics within the cluster. They may have been, at various points in the cluster's orbital history, launching individual stars out of the galaxy entirely. The invisible population within the cluster, the central IMBH and the retinue of stellar mass black holes surrounding it, has left its signature not only in the cluster's internal structure, but in the wider galactic environment, in the form of stars racing at hundreds of kilometers per second through the Milky Way's halo, tracing an orbital history written in the velocities of objects launched by the most extreme gravitational interactions the galaxy has ever seen. This is what it means to say that the absence of something can shape everything around it. The black holes in Omega Centauri have determined the cluster's core structure, influenced the dynamics of stars across billions of years, potentially contributed to the population of hypervelocity stars in the galactic halo, and are, even now, in the invisible encounters happening in the cluster's dense core, producing the black hole binary systems that will eventually merge and announce their existence to gravitational wave detectors tens or hundreds of millions of years from now. The discovery of OmegaCat BH2 is not just the discovery of one black hole in one star cluster. It is the first direct observational glimpse into a system that has been operating as a black hole factory for 12 billion years, producing the gravitational wave signal of the future from the stellar deaths of the distant past. But there is something else in this story, something that the paper's authors raise almost in passing, and that deserves considerably more attention than the formal language of a scientific publication can give it. Something that cuts at the reliability of the models themselves, and that could change the quantitative predictions that the gravitational wave community is currently building their instruments to test, the problem of the lower than expected mass. Let us return to it, because it is the loose thread that, if pulled, might unravel some of our most confident assumptions. The theoretical predictions for the masses of black holes formed from core collapse supernovae in metal-poor environments like Omega Centauri come from stellar evolution and supernova models that have been calibrated primarily against observations of objects in solar metallicity environments. The Milky Way's field population of black holes, the X-ray binaries that have provided most of our observational constraints on stellar mass black hole masses, the isolated black holes found through gravitational microlensing. These are, for the most part, objects formed from stars with roughly solar metallicity. The extension of the models to very low metallicity environments is, to a significant degree, theoretical extrapolation. The prediction that low metallicity stars produce more massive black holes rests on the stellar wind argument. At low metallicity, massive stars have weaker radiation-driven winds, lose less mass during their main sequence and post-main sequence evolution, and arrive at the moment of core collapse with larger amounts of material available to form the compact remnant. This argument is well supported by theoretical models of stellar winds, but stellar wind theory is not the only physics that determines the mass of a black hole remnant. The dynamics of the core collapse supernova itself, the propagation of the shock wave through the collapsing stellar interior, the role of neutrino energy deposition in driving or failing to drive a successful explosion, the possible formation of a proto-neutron star that subsequently collapses to a black hole if accretion continues, are governed by a completely different set of physical processes. And these supernova dynamics at low metallicity are less well understood observationally. If some fraction of core collapse supernovae at low metallicity produce unexpectedly low-mass black holes, through some process that enhances the efficiency of mass ejection during the explosion, or that truncates the mass of the collapsing core before the final black hole forms, then our theoretical predictions for the mass function of black holes in metal-poor globular clusters, like Omega Centauri, could be systematically wrong. The 446 solar mass of Omega Cat BH2 does not prove this. One data point is not a mass function, but it is the first direct measurement of a black hole mass in Omega Centauri, and it points in an unexpected direction, and that is the kind of data point that demands a theoretical response. We now know that a metal-poor star is able to form a black hole like this, and we need to figure out how that happens, said Anil Seth. This is not a statement of puzzlement. It is a research agenda. And the answers to that research agenda, when they come, will change our understanding of how black holes form across cosmic history. In the metal-poor environments that dominated the early universe when the stars were young and the galaxy was assembling itself, the stakes of understanding this are not confined to Omega Centauri, or even to globular clusters. The early universe was globally metal-poor. The first stars, the population 3 stars that formed from pristine hydrogen and helium gas in the first 100 million years after the Big Bang, were almost entirely metal-free. The black holes they produced were, according to our current models, much more massive than any stellar mass black hole known today, possibly ranging into the hundreds or even thousands of solar masses. These first-generation black holes are the seeds from which the first quasars grew, the building blocks from which the supermassive black holes at the centres of today's galaxies were assembled over billions of years of accretion and merging. Understanding how metal-poor stars produce black holes, at what mass, with what distribution, through what mechanisms, is the first step in the chain of understanding that eventually leads to the origin of the supermassive black holes themselves. Omega Centauri, a relic of the early universe, frozen in time at 12 billion years old and sitting only 18,000 light-years away, is arguably the best available laboratory for this question. Its stellar population represents the chemistry of the early universe. Its black hole population represents the death toll of that chemistry. And now, for the first time, we have actually found and characterized one of those black holes. One out of an estimated 10,000. Science earns credibility through exactitude. and exactitude in astrophysics is won not merely by making a measurement, but by understanding everything that could make that measurement wrong. The discovery of Omega Cat BH2 is the most important observational black hole result in globular cluster astronomy in a decade. It is also a result built on a foundation of inference, a foundation that the authors of the discovery paper were careful to lay with full transparency, and that deserves examination precisely because the strength of that foundation determines how much weight the discovery can bear as science builds upon it. The central claim is this: a main sequence turn-off star in Omega Centauri is orbiting an invisible companion with a mass of 4.46 solar masses, and this mass is too high to be a neutron star, therefore the companion is a stellar mass black hole. Let us examine each link in this chain of reasoning. The first link is the observational claim. The star is moving in a way inconsistent with simple proper motion through the cluster. This link is the strongest in the chain. The Omega Cat Hubble dataset, 351 epochs spanning 20.6 years, is the highest quality astrometric dataset for any galactic globular cluster ever assembled. The JWST data adds 12 additional epochs at the end of the baseline at a phase in the orbit, periastron, where the astrometric signal is largest. The statistical significance of the astrometric detection is high. Independent reductions of subsets of the same data by the Plate et al. Group had already identified this star as an astrometric binary candidate. The observational case that this star is in a binary system, that its motion on the sky is not simply linear proper motion, but a curve consistent with orbital acceleration, is not in question. The second link is the determination of the companion's mass from the orbital fit. This is where the uncertainties are most significant, and where the authors are most careful. The orbital fitting procedure is a Bayesian MCMC analysis that simultaneously optimizes over 8 orbital parameters: the period, eccentricity, inclination, argument of periastron, time of periastron passage, semi-major axis, and the 2 components of the system's proper motion in the cluster, constrained by the astrometric data, by a prior on the star's velocity within the cluster derived from dynamical simulations, and by the known mass of the visible star derived from its photometric and spectroscopic properties. The crucial subtlety in this fitting is the orbital period uncertainty. The observational baseline is approximately 23 years. The best fit orbital period is 94 years, meaning that even the full 23-year observational baseline covers only about 1/4 of the orbit. The astrometric data were obtained during periastron, when the star was moving fastest and the astrometric signal was largest. This fortunate circumstance means that even though only a fraction of the orbit is observed, the constraint on the orbital parameters, particularly the combination of period, semi-major axis, and eccentricity that determines the black hole mass, is tighter than it would be if the observations had been obtained at some random phrases. The mass constraint is stated as 446 plus 1.22 deflants 1.01 solar masses, a range of roughly 3, 5 to 5.7 solar masses at 1 sigma. This is well above the maximum neutron star mass, approximately 2.5 to 3 solar masses, depending on the equation of state of dense nuclear matter, confirming the black hole interpretation. But the period uncertainty is substantial, 94 years with a range from perhaps 52 to 157 years at reasonable confidence. This uncertainty propagates into uncertainty in the orbital phase, and consequently into uncertainty in which part of the orbit was being observed during the 23-year measurement window. The authors treat this carefully, showing that across the posterior distribution of orbital solutions, the mass constraint is consistently above the neutron star mass threshold. But the inference is probabilistic. It is not a single clean measurement of mass, in the way that, say, a high-precision radial velocity solution with many complete orbital cycles would be. It is the best fit interpretation of a rich but incomplete dataset. The third link is the classification of the companion as a black hole rather than some other dark object. The mass constraint rules out a neutron star. What else could produce a mass of 4.46 solar masses in a dark compact object? The options are limited. A pair of neutron stars, bound to each other in a tight inner binary, could in principle contribute a combined mass above the single neutron star maximum, but such a configuration would be extremely unusual dynamically, would likely be radio bright as a binary pulsar, and has not been proposed seriously as an explanation for this system. A very dark, massive white dwarf is not possible above approximately 4 solar masses, the Chandrasekhar limit beyond which electron degeneracy pressure cannot support the object against gravitational collapse. A collection of very faint stars in a tight cluster is not consistent with the photometric evidence, which shows the visible star to be the brightest object in its immediate neighbourhood. A primordial black hole, a black hole formed not from stellar collapse but from density fluctuations in the early universe, cannot be excluded on purely theoretical grounds, but primordial black holes in this mass range would already be well into their evaporation phase through Hawking radiation and would not survive to the present day. The black hole interpretation is not merely the most plausible, it is, to current knowledge, the only physically consistent interpretation of an invisible non-accreting compact object with a mass above 3.5 solar masses. There is, however, one source of systematic uncertainty that is worth flagging explicitly, because it could in principle affect the mass determination, the unknown orbital inclination. Astrometry, unlike radial velocity spectroscopy, measures the motion of the star in the plane of the sky, the two-dimensional projection of the true three-dimensional orbit. For a face-on orbit, the full three-dimensional motion is in the plane of the sky and the astrometric measurement captures all of it. For an edge-on orbit, the star moves partly toward and away from us, and the astrometric measurement captures only the component of motion projected onto the sky. Astrometry is sensitive to orbital inclination through the shape of the projected orbital ellipse on the sky. A circular orbit appears as an ellipse when seen at an angle, and the eccentricity of the apparent ellipse carries information about the inclination. The MCMC fit constrains the inclination along with the other orbital parameters, but the inclination is one of the less precisely constrained parameters, and its uncertainty contributes to the uncertainty in the black hole mass. The reported mass range accounts for this inclination uncertainty, but it is important to understand that the mass determination is not inclination independent. The multi-wavelength constraints, the Deep Chandra X-ray non-detection, and the Australia Telescope Compact Array radio non-detection are entirely consistent with the black hole interpretation. A 46 solar mass black hole in a wide 94-year orbit with a 0.78 solar mass main sequence companion should produce essentially no detectable X-ray or radio emission through accretion because the stellar wind from the companion at this orbital separation is far too thin and far too slow to drive meaningful mass transfer. The non-detections are expected. They provide consistency checks rather than independent evidence for the black hole. The question of whether OmegaCat BH2 is a fair representative sample of the cluster's black hole population, whether the method biases toward finding black holes with particular masses or orbital parameters, is acknowledged as an important caveat by the authors. Wide orbital period binaries are more accessible to the astrometric method than short period ones, because the projected orbital motion on the sky is larger for wider separations. Low-mass black holes are less accessible than high-mass ones because the amplitude of the reflex motion of the visible star, the stellar wobble that astrometry detects, scales with the mass ratio between the companion and the total system mass. A more massive black hole will produce a larger wobble in the same visible star, making it easier to detect. The fact that the first detection happens to be a relatively low-mass black hole in a wide orbit is therefore surprising in the context of the detection bias. It might have been expected that the first detection would be a more massive black hole, inducing a larger and more easily detectable wobble. The fact that the first one found is near the low-mass end suggests either that the true mass distribution of black holes in Omega Centauri is weighted toward lower masses, or that the search method is more sensitive to wide orbits at low masses than the simple scaling argument suggests. or that this particular detection involved a favourable combination of orbital phase, inclination, and timing that made it exceptionally accessible despite its low mass. Distinguishing among these explanations requires more detections, and more detections are coming. The OmegaCat team has stated explicitly that this is the first result from a larger ongoing search for astrometric binaries in Omega Centauri, and that a systematic analysis of the broader binary population, black hole binaries, neutron star binaries, white dwarf binaries, double main sequence binaries, will be presented in a forthcoming comprehensive paper. The results of that analysis will tell us, for the first time, whether the black hole binary population in Omega Centauri is consistent with the numbers predicted by the dynamical simulations, whether the period distribution matches what the cluster Monte Carlo models produce, whether the companion star masses follow the theoretical predictions, whether there are additional black hole binaries hiding in parts of the parameter space that the current search has already swept, or whether the sensitivity is limited in ways that leave large portions of the population unexplored. This is the frontier state of the science as of 2026, not a clean conclusion, not a triumphant final answer. A first detection extraordinarily significant in what it demonstrates and what it implies, but sitting at the beginning of a survey rather than at its end. A data point that confirms the theoretical framework while simultaneously introducing new puzzles about black hole masses. A discovery that opens more questions than it closes. And then there is the question that haunts the edges of everything we have discussed. The question that the paper does not address because it lies outside the scope of the measurement, but that no thoughtful consideration of this discovery can avoid. What does it mean that these black holes exist in such extraordinary numbers, invisible and patient, in the oldest structures in our galaxy? What is the physics of a place that has been generating and accumulating stellar corpses for 12 billion years? And what happens, in the fullness of time, when the accumulated gravitational interactions in that place begin to produce mergers? Not just the merger of OmegaCat BH2 with its future tidal disruption partner, but the mergers of black holes with black holes, the most violent and energetically extreme events in the universe, accessible to current detection. The Nancy Grace Roman Space Telescope is scheduled to launch on August 30, 2026. At the time this documentary is being written, the telescope's primary mirror is polished, its detectors are cooled to their operating temperature, its launch vehicle is prepared. Roman is a 2.4-metre telescope, the same primary mirror diameter as Hubble, but with a field of view 100 times larger, 0.28 square degrees compared to Hubble's 0.003 square degrees. This enormous field of view, combined with Hubble comparable resolution and deep sensitivity in the near-infrared, will allow Roman to do something Hubble cannot: survey the densely crowded central regions of the Milky Way, the galactic bulge, teeming with hundreds of millions of stars, at high spatial resolution, with a regular observational cadence, year after year. Matthew Whitaker, in the official announcement of the OmegaCat BH2 discovery, named Roman explicitly as the next instrument of opportunity for finding black hole binary systems like the one just discovered. We're also very excited for the launch of NASA's Nancy Grace Roman Space Telescope because it will image the crowded galactic bulge, including the galactic center, very regularly with Hubble-like resolution and with a much wider field of view. We're hoping we'll be able to find black hole binary systems like this one because of the regular cadence of Roman's observations. Roman will not merely continue Hubble's astrometric work, it will transform the scale of it. Where Hubble's surveys of Omega Centauri required 20 years to accumulate a statistically useful baseline and covered a specific, relatively small field centered on the cluster, Roman will be able to survey much larger areas of the sky, including not just Omega Centauri, but dozens of other globular clusters in the Milky Way's bulge region, regions where the number of background stars available for astrometric reference is much higher, allowing even more precise measurement of individual star motions. Roman's galactic bulge survey designed to detect thousands of gravitational microlensing events from compact objects including black holes, free-floating planets, and neutron stars, will also accumulate the multi-epoch astrometric data needed to search for binary systems with dark, massive companions throughout the densest stellar environments in the galaxy. The gravitational microlensing component of Roman's science program is independently significant for black hole detection. Microlensing, the transient brightening of a background star as a massive foreground object passes in front of it, bending and magnifying the background star's light through gravitational lensing, has been used to detect individual isolated stellar mass black holes in the galactic field. The first confirmed detection of an isolated free-floating stellar mass black hole using microlensing was published in 2022 based on Hubble Space Telescope astrometric follow-up of a microlensing event first detected by ground-based surveys. The black hole's mass was determined to be approximately 7 solar masses, and it was moving through the galaxy entirely alone. No stellar companion, no accretion disk, no electromagnetic signature of any kind. Its presence was revealed only by the way it bent the light of a more distant star in the galactic bulge as it drifted in front of it. Roman will detect thousands of such events per year, building a statistical sample of isolated black holes in the galactic field that will constrain the mass function of stellar mass black holes across the galaxy's stellar population in a way that is simply not achievable with any other method. This combined program, astrometric binary searches for black holes in globular clusters, microlensing searches for isolated field black holes, and the continued analysis of archival Hubble data using the methods developed for OmegaCat BH2, will, within the next 10 years, produce a black hole census of a quality and depth that currently seems almost utopian. The theoretical models will be tested against real data. The predictions of the cluster Monte Carlo simulations, the 10,000 black holes in Omega Centauri, the hundreds of thousands across all Milky Way globular clusters, will either be confirmed or revised in the light of actual observations. The connection between globular cluster black hole populations and the gravitational wave events detected by LIGO and its successors will move from theoretical argument to empirical constraint. The LIGO scientific collaboration has been operating its advanced LIGO detectors at increasing sensitivity since their first science run in 2015. The fourth observing run, 04, which concluded in 2025, produced more than 200 gravitational wave event candidates, a rate of detection that was unimaginable when the first signal was announced in February 2016. The planned upgrades for 05 and beyond, including the implementation of quantum squeezing and improved mirror coatings, will push the detection horizon out to cosmological distances and increase the volume of the universe accessible to gravitational wave astronomy by factors of several. The planned next-generation detectors, Einstein Telescope in Europe, Cosmic Explorer in the United States, will within the next 2 decades extend the gravitational wave horizon to essentially the entire observable universe, capable of detecting the merger of 2 stellar mass black holes anywhere in the universe's history, including in the early universe when the first massive stars were dying and the first black holes were forming. The question of where the black holes in LIGO's event catalogue come from, globular clusters, field binaries, or nuclear star clusters, will be resolved, at least in statistical terms, within this decade, and the resolution will depend critically on the observational census of black hole populations in real clusters, a census that OmegaCat BH2 has just begun. If the true mass distribution of black holes in globular clusters is systematically lower than the models predict, if Omega Centauri's first detection, at 4.46 solar masses, is representative of a population weighted toward low masses, rather than the high masses seen in many LIGO events, then globular clusters may contribute less to the high mass end of the LIGO event rate than the theoretical models currently suggest. If the mass distribution is consistent with the models, then the connection is strengthened. The James Webb Space Telescope, still operating in 2026 and expected to continue operations for at least another decade, will play its own role in this story. The contribution of JWST data to the OmegaCat BH2 discovery was not merely technical. The additional precision at the periastron phase that sharpened the mass constraint. It was demonstrative. JWST's near-infrared sensitivity and angular resolution make it a powerful complement to Hubble's optical astrometry for dense, reddened, crowded stellar environments. Future combined Hubble JWST or Roman JWST analyses of globular clusters in the inner galaxy, where dust extinction makes optical observations difficult, will extend the accessible parameter space for black hole binary searches to environments that current surveys cannot reach. There is also a fourth telescope that belongs in this story, whose contribution to the overall program of black hole discovery has been quietly remarkable, and whose future role is potentially transformative. The European Space Agency's Gaia mission, a satellite launched in 2013 and still operating in its extended mission phase, has been conducting the most comprehensive astrometric survey of the Milky Way ever undertaken, measuring the positions, proper motions and parallaxes of nearly 2 billion stars with micro-arcsecond precision. The Gaia black hole discoveries have been remarkable. Gaia BH1, announced in 2022, is a 9.6 solar mass black hole in a 186-day orbit with a Sun-like star located only about 1,600 light-years from Earth. Gaia BH2, announced in 2023, hosts a 8.9 solar mass black hole, and Gaia BH3, the most dramatic of the three, is a 32.7 solar mass black hole, the most massive stellar mass black hole ever found in our galaxy, in an 11.6-year orbit with a low metallicity giant star at a distance of only 2,000 light-years. Gaia BH3's metallicity is extraordinarily low, at roughly 1/3 of the solar value. It is among the most metal-poor stars known in the galaxy, and its black hole companion, at 32.7 solar masses, is exactly what the theoretical models predict for a black hole formed from a metal-poor massive star, heavy because the progenitor's weak stellar winds left behind most of its mass at the time of collapse. Gaia BH3 is the observational validation of the low metallicity, high mass remnant prediction, the very prediction that OmegaCat BH2 appears to violate. This is a genuine puzzle. Gaia BH3, 32.7 solar masses, metal poor. OmegaCat BH2, 446 solar masses, metal poor. Both formed from stars in low metallicity environments, both at the low metallicity end of the stellar population. Radically different masses. If the theoretical prediction that low metallicity produces high black hole masses is correct, then one of these objects is an outlier. If both are representative, then the mass function of black holes in metal-poor environments is much broader than the current models suggest, spanning from below 5 to above 30 solar masses, which has significant implications for the gravitational wave interpretation. Alternatively, there is a subtlety in the comparison that the current data cannot fully resolve. We do not know the exact metallicity of the progenitor star of OmegaCat BH2 within Omega Centauri. The cluster has multiple stellar populations spanning a range of metallicities, from extremely metal-poor early-generation stars to more metal-enriched later-generation stars. If the progenitor of OmegaCat BH2 belonged to a later generation, more metal-rich subpopulation, then its low remnant mass would be less anomalous. It would simply reflect the higher mass loss appropriate for a star of that metallicity. Determining the metallicity of the progenitor is impossible after the fact. The black hole carries no chemical signature, and the visible star, having formed separately and been dynamically captured into the binary, tells us nothing about the chemical history of the black hole's progenitor. This uncertainty is a fundamental limitation of the dynamical binary formation scenario, and it cannot be resolved with current or near-future data. What can be resolved in the near future is whether OmegaCat BH2 is an isolated outlier in the Omega Centauri black hole mass function, or the representative of a broad low-mass population. The ongoing OmegaCat binary search, the Roman survey, the continued Gaia data releases, and their extended astrometric mission, and the accumulation of LIGO events with well-determined mass functions will, within the next decade, provide enough data to address this question statistically. The theoretical models will be revised, refined, or replaced. The census will be taken, and the picture that emerges will be a sharper, more accurate representation of what the universe's oldest gravitational factories have been producing, and what they will continue to produce for billions of years to come. There is one more thread to pull before this story can be left at its proper horizon. A thread that connects the technical achievements of astrometry and orbital fitting to the most fundamental question in black hole physics, a question that has occupied theorists since the 1970s, and that the detection of more and more isolated, quiescent black holes makes more experimentally relevant by the year. It is the question of what black holes actually are, in the deepest physical sense. Not how they form, or how they influence their surroundings, but what happens at their centres, and whether the information about everything that has ever fallen into them is truly lost, or whether it escapes in some form we do not yet understand. Stephen Hawking showed in 1974 that black holes are not entirely black. Quantum mechanics predicts that near the event horizon, pairs of virtual particles, a particle and its antiparticle, fleetingly created from the quantum vacuum, can be separated by the horizon before they annihilate each other. One particle falls in, the other escapes as radiation. The black hole slowly loses mass over timescales that are astronomically long for stellar mass objects. On the order of 10 fat years for a black hole of a few solar masses, longer by many orders of magnitude than the current age of the universe, but finite. In principle, a black hole will eventually evaporate completely through this Hawking radiation, leaving behind nothing but a thermal bath of photons and other particles. And the information carried by everything that ever fell into the black hole, every atom, every photon, every quantum state of every particle that crossed the event horizon over the black hole's lifetime, will be, if Hawking's original calculation is taken at face value, entirely scrambled and thermally smeared, unrecoverable from the outgoing radiation. This is the information paradox. It is a genuine crisis in theoretical physics, a place where quantum mechanics and general relativity come into direct conflict, where one of the two foundational theories of modern physics must, if the other is to be trusted, be wrong in some important way. Subsequent work by Juan Maldacena, Don Page, and many others has suggested that Hawking radiation must in fact carry information, must be subtly non-thermal, must encode in some complex way the quantum state of everything the black hole has absorbed. But the precise mechanism by which this happens is not understood. It is one of the great unsolved problems in all of physics. The relevance of OmegaCat BH2 and objects like it to the information paradox is not direct. A 446 solar mass black hole in a wide, non-accreting binary is not going to resolve the information paradox by radiating, but the accumulation of a comprehensive, observationally constrained census of stellar mass black holes in globular clusters, their masses, their binary properties, their environments, provides a foundation for the future experimental study of black hole physics in ways that are not yet fully imaginable. Every confirmed, well-characterized black hole is a data point in the cosmic inventory of the universe's most extreme objects. Everyone adds to the observational foundation that theoretical physics must eventually explain, completely and consistently within a single unified framework. The black hole at the center of OmegaCat BH2 formed 12 billion years ago, in the death of a massive star in a galaxy that no longer exists. It is 46 times the mass of the Sun, compressed into a region smaller than a city. It produces no radiation. It affects nothing it does not touch with gravity. It has been drifting through the stellar crowd of Omega Centauri ever since it formed, undetected, undetectable, patient, until 2026, when the accumulated patience of a different kind, 23 years of pixels on a space telescope's detectors, made it visible at last. Not visible in the sense of producing light. Visible in the sense of leaving a trace in the motion of the star it holds. John Michel predicted this in 1783. before the existence of telescopes powerful enough to test his prediction, before the discovery of general relativity, before the confirmation that stars produce black holes when they collapse. He said, "Look at what moves around the dark thing, and you will know the dark thing is there." He was right. It just took 243 years to build the instruments capable of acting on the advice. There is a star 18,000 light-years away that has been dancing for hundreds of millions of years with something it cannot see. The star does not know this, of course. It does not know anything. It follows the arc of its orbit as all objects do, helplessly, beautifully, in obedience to the mathematics of curved space-time. It sweeps inward toward its dark companion at periastron with a velocity that peaks at something on the order of several kilometers per second. It swings outward on its 31 astronomical unit semi-major axis, reaching its greatest separation, moving at its slowest before gravity curves it back. In 94 years, more or less, give or take the uncertainties that honest science never hides, it completes one full loop and begins again. It has been doing this since long before anyone on this planet learned to write. It will be doing this long after whatever civilization follows ours has forgotten that we existed, until the day, coming in roughly 800 million years, if the models are right, when a chance encounter with another massive body in the cluster core breaks the gravitational partnership, sends the star tumbling in one direction and the black hole tumbling in another, and returns both objects to the anonymous dark of the cluster. A brief arrangement, dissolving, like all arrangements in the universe. What moves me most about this discovery, and I do not use move as a figure of speech, I mean it in the sense of something that rearranged a small but important part of how I understand the universe to be, is not the technology required to make it. It is not the precision of the measurement, though the measurement is almost incomprehensibly precise. It is not even the fact that we found the first of 10,000 invisible objects that should have been there all along. What moves me is the duration. Hubble went into orbit in 1990. The first observations of Omega Centauri that would eventually contribute to this discovery were taken in 2002. The last observations included in the analysis were taken in 2025. Astronomers who began careers as graduate students when this data collection started are now senior researchers. The teams who designed the instruments that made these measurements are in some cases no longer alive. The discovery was made not by any single act of insight or heroism, but by the slow, patient, cumulative effort of hundreds of people over more than 20 years, each one adding a small increment to a dataset that no individual observer could have known would yield what it ultimately yielded. This is the deepest human truth inside this scientific story. The universe is not obligated to reveal itself on timescales convenient for individual human lives. Many of the most important things we now know about the cosmos required observations that span decades, generations, careers. The 94-year orbital period of OmegaCat BH2 is longer than a human lifetime. The 12 billion-year age of Omega Centauri is 1 trillion times longer than a human lifetime. The patience required to study things that move and evolve on these timescales is not a patience that any individual possesses. It is a patience that science possesses as an institution, as a multi-generational, self-correcting, archive-building collective endeavour that outlasts any of its individual contributors. That is not a merely consoling thought. It is the literal mechanism by which this discovery was made. The 23 years of Hubble data that characterized one black hole were not gathered by one team for one purpose. They were gathered by dozens of different teams for dozens of different scientific purposes over more than 2 decades, stored in an archive that remained accessible long after the individual programs that generated them had concluded. The OmegaCat team did not observe Omega Centauri for 23 years to find this black hole. They went into the archive, where the observations were waiting, and found something that the original observers had no way of knowing was there. The archive is the instrument. The patience is distributed across the entire community. The discovery belongs to everyone who ever pointed Hubble at Omega Centauri, and faithfully calibrated their data and submitted it to the repository. There are 9,999 more black holes estimated to be lurking in Omega Centauri, 9,999 objects, each one a 4 to maybe 30 solar mass singularity, orbiting in the dark, moving through the stellar crowd, some of them in transient binary partnerships with normal stars, most of them entirely alone. The methods that found the first one are already being used to search for more. Roman will launch this month. JWST continues to operate. The archive continues to grow. The 23-year baseline that was sufficient to find one will, in time, extend to 30 years, 40 years, half a century. The additional temporal leverage will open up longer period orbits, wider separations, fainter companions. The census will be taken, and when the census is substantially complete, when we have, say, 100 black hole binaries characterized in detail in Omega Centauri alone, with known masses, orbital periods, eccentricities, companion types, the theoretical models will be tested at a precision that is currently unimaginable. The gravitational wave predictions will be sharpened. The stellar evolution models for metal-poor environments will be constrained. The history of a galaxy that was devoured 12 billion years ago will be partially reconstructed from the masses and distributions of its stellar ghosts. All of this from one star, tracing one slow orbit around something that isn't there. In 1783, John Michell described the dark star in terms that were remarkably close to what we now call a black hole. He could not see one, he could not prove that one existed, but he could reason toward the consequences of one's existence. And he could describe the method, watching the motion of a luminous companion, by which it might someday be found. He died in 1793, 1 decade after writing those words, 10 years before the Battle of Trafalgar, 233 years before Hubble first flew, 243 years before Whittaker and Seth and Heberle, and their colleagues looked at 351 data points spread over 20 years and said, "The star is moving in a curve. Something is pulling at it that we cannot see. We can tell you exactly how heavy that thing is. The dark star that Michell imagined is real. It is 18,000 light-years away. It weighs 4.46 times the mass of the Sun. It will never be visible, and it has been there, patient and invisible, since before the Earth was formed we found it. Not because we went looking, exactly, but because we had the patience to keep building the archive, keep refining the methods, keep asking whether the thing that theory required might finally be accessible to measurement. Not because any single person had a sufficient career to observe it, but because the institution of science is older than any career, and the archive is longer than any lifetime. The universe has been keeping this secret for 12 billion years. We have been looking for it for 40 years with space telescopes, and 20 years with the specific data that finally gave it away. In cosmic terms, that is barely the blink of an eye. In human terms, it is everything. What are the other 9,999 black holes doing right now, in the dark, in the silence, in the ancient stellar crowd of Omega Centauri? Some of them are forming binaries with stars they have never met before. Some of them are breaking apart binaries they formed 100 million years ago. Some of them are spiraling, in very tight orbits with other black holes, losing energy to gravitational radiation at a rate too low to measure, but too constant to stop. Each orbit slightly shorter than the last, each year bringing the two singularities fractionally closer to the merger that will send a ripple across 1 billion light-years of space-time to be heard, perhaps, by a detector that does not yet exist, operated by hands that have not yet been born. The discovery of a megacat BH2 is not an ending. It is not even a beginning, really. It is the first verification that the question we have been asking has an answer we can actually reach. The rest of the answer is still out there, waiting, in the dark, orbiting something that isn't there, until the day we are patient enough, and precise enough, and stubborn enough to find it.